In this lecture, we are going to learn about rotational motion and gravitation. As you know, Moon rotates around Earth. Earth rotates around the Sun. All planets rotate around the Sun. On the other hand, if we go to the microscopic domain, electrons rotate around the nuclei in the atoms. Motion in general can be either translational or rotational. In the past chapters of the course, we learned all about translational motion. In this chapter, we are going to learn about the physics of rotational motion and also about gravitation. Very well. So now we are ready to start learning about rotational motion and gravitation. Just like we did for translational motion, we repeat the same story here. We start with the kinematics. We start introducing the variables of motion. For translational motion, the change in position was represented by delta x. For angular motion, the change now will be an angular displacement, delta theta. Usually we use theta to represent the angular displacement, just like we use x to represent the linear displacement. Then the velocity v goes into omega, the variable that we use for angular velocity is omega. And for the acceleration, rather than a, which we use for linear motion, we use alpha for the angular motion, for the angular acceleration. During the angular motion or rotational motion, we'll be dealing with the circumference of the orbit, 2 pi r. Any orbit will have some radius r, and as you know from geometry, the circumference of such an orbit is equal to 2 pi r. So S here represents the length of the arc, which is for a full rotation is 2 pi r. If we divide both sides by r, we get S over r equals 2 pi. So when the arc is one full rotation, the angle now is 2 pi. The angular displacement, delta theta, is 2 pi. As we know from geometry, one complete rotation is equivalent to 360 degrees. Therefore, 2 pi is equivalent to 360 degrees. The unit that we use for angular displacement is called radian. So here 2 pi radians, this is the angular displacement. This is equivalent to 360 degrees. Therefore, 1 pi is equivalent to 180 degrees, and half pi is equivalent to 90 degrees. We will need this information when we convert between radians and degrees. In general, if you consider an angular motion or rotational motion like this motion, some object is rotating in an orbit here. It started along the x-axis, and after some time Now you have an angle theta. This is the angular displacement. The radius for the orbit is constant. The radius is constant. But the length of the r in general changes. The arc S may change. When S is equal to r, when the arc length is equal to the radius, then S divided by r, when they are equal, this is 1. This is 1. So 1 radian, when the angle is 1 radian, this means the length of the arc is equal to the radius of the orbit. This is the unit used in the SI system for angular displacement. We call it radians, or in short, rad. So 1 rad means an angle with an arc S equal to the radius of the orbit. In degrees, 1 rad is equivalent to 57.3 degrees. 1 rad is equivalent to 57.3 degrees. Example, convert 45 degrees to radians. We know that 180 degrees is equivalent to pi radians. Therefore, we apply proportionality. So 45 divided by 180 multiplied by pi, this is 1/4 pi. So 45 degrees is equivalent to pi over 4 radian. You can substitute for pi 3.14. We know that value. Divide 3.14 by 4, you get the numerical value, the numerical angle in radian that is equivalent to 45 degrees. Usually, when we study rotational motion, we need a reference line, and usually the reference line is taking the horizontal x-axis. We start measuring the angle from that reference line. As time propagates, the object moves in this circular path, and the angular displacement increases, changes. Suppose the initial angle was theta I for initial. The final angle was theta F for final. So delta theta, the angular displacement, is equal to theta F minus theta I. Always delta theta is measured in radians. So the default here for the unit in the SI system is radian. If you want to use another unit like revolution, then we know that 1 revolution is equivalent to 2 pi radians, or to 360 degrees. But these are not SI units. The SI unit for angular displacement is the radian, or rad. Example, the initial angle was 4 radian, the final angle is 7 radian, therefore the angular displacement is 7 minus 4, and this is 3 radians. We move on to learn about the angular velocity. Angular velocity is defined as the change in the angular displacement per unit time. The change in the angular displacement, the change in the angle, divided by the change in time, delta theta by delta t. Delta theta is measured in radian, and delta t is measured in seconds. So the unit for the angular velocity, the unit in the SI system is radian per second, or rad per second. This is an average value. In other words, the initial time is different from the final time. However, if we are interested in the instantaneous value for the angular acceleration, then we need to take the limit when TF is very near to TI, or the change in time is almost zero. That limit will allow us to calculate the instantaneous angular velocity. Example: the rotor on a helicopter turns at an angular velocity of 320 revolutions per minute. We use this mnemonic, rev per min, which means revolutions per minute. Express this angular velocity in radians per second. If the rotor has a radius of 2 meters, what arc length does the tip of the blade trace out in 300 seconds? The pilot opens the throttle and the angular velocity of the blade increases while rotating 26 times in 3.6 seconds. Calculate the average angular velocity during that time. This is a simple question meant only to sharpen our skills when we deal with these definitions with the conversion between units. So for the first part, we need the angular velocity in radians per second. We have 320 revolutions per minute, 320 revolutions per minute. The conversion factor, each revolution has 2 pi radians. So 2 pi radians divided by 1 revolution, this is just 1. All conversion factors must be 1. And then 1 minute is equivalent to 60 seconds. So this is another conversion factor 1. So now minute cancels with minute, revolution cancels with revolutions. And when you evaluate these numbers here, it is 33.5 radians per second. This is how we convert from revolution per minute to radian per second. Please take note of that. Simple, straightforward procedure. You need just to multiply by the proper conversion factor to go from revolution to radians and from minutes to seconds. Then for the second part, if the rotor has a radius of 2 meters, so R is 2 meters, what arc length does the tip of the blade trace out in 300 seconds? Delta theta equals omega t, just like linear motion, x delta x equals vt. So instead of v, you have omega here. We calculated omega in the first part, 33.5 radian per second, and t is 300 seconds. So the answer is 1.01 by 10 to the power 4 radian. You see, the angle, the angular displacement is measured in radians. Second here cancels with second there. Then the arc length, from the definition of the angular displacement, the arc length delta S is equal to R delta theta. R is 2 meters. This is SI unit. We don't need to do any changes there. And the angular displacement is 1.01 by 10 to the power 4 radian. Therefore, the arc length is 2.02 by 10 to the power 4 meters. Then for the third part, we have now the angle. We have 26 revolutions, and each revolution has 2 pi radians. So this corresponds to 52 pi radians. We divide this by the elapsed time, delta theta divided by delta t, 52 pi divided by 3.6 seconds. This is 45 radian per second. This is the new velocity, the new average velocity. Whenever you have a rotating object like this wheel here, as you change the angular velocity from some initial value omega I at initial time ti to some final value omega f at some final time tf, then we can calculate the angular acceleration, the average angular acceleration. It is the change in the angular velocity per unit time. The change in the angular velocity, omega f minus omega I, this is the change in the angular velocity. We divide that by the time, just like we did for translational motion. For translational motion, the acceleration A is equal to delta V divided by delta T. So rather than delta V here, we have delta omega. For rotational motion, we have angular velocity. We divide that by the change in time to get the angular acceleration. Again, this is the average angular acceleration, and we can get the instantaneous value by allowing the time here, the change in time, to go to 0. Example, the initial angular velocity is 15 radian per second. The final angular velocity is 9 radian per second. The elapsed time is 3 seconds. Therefore, the angular acceleration, delta omega by delta t, 9 minus 15 divided by 3 seconds. This is minus 2 radian per second squared. So just like linear motion, we are dealing with vector quantities. It can be positive or it can be negative. As I said earlier, if it is clockwise, usually it is negative. If it is counterclockwise, the rotation, then it is positive by convention. This is the instantaneous acceleration. You need just to take the value delta omega by delta t when the change in time is very small.